Hello, I'm Yashil Ramesh, and welcome to my oscillations physics lab for lab 4. So let's get started. So the purpose of this lab is to investigate the motion of a spring mass system with the mass oscillating in an arc. And so what do we use to do this? We use the tracker software to track the observed position through our video. We use GlowScript as a computational model, and the goal is to determine whether the model follows the energy principle. And so the result that we ended up getting, which we'll show throughout this lab, is the system's total energy remains constant at 0, thus falling in line with the energy principle. So what are our fundamental principles? Well, we have Newton's second law, which is the system's change in motion is proportional to the net force applied. And so we can look at this as F net is going to be equal to the change in momentum over the change in time. And so we can go and expand that because we know that our force in this instance is a harmonic motion or a pendulum force. And I can go ahead and expand that, but we'll leave that for later because we'll see that through our tracker software. We also have the energy principle, which states that the change in energy is, So that states that our change in energy is going to be equal to the work done, or the work plus Q. And so some useful equations would be the update formulas derived by Newton's second law. So we can look at velocity update, for instance, which looks like this. Let's go ahead and get rid of this real quick. And so the velocity update formula is going to be V final is equal to V initial plus F net over M times the change in time. And then we also have position update, which looks very similar to this, but we're just taking our force plus our velocity average over time. And there's going to be some more useful equations that we use throughout this, and we'll take a look at those as we get to them throughout this lab. So first, let's take a look at what we got for our tracker data. So here you can see our actual system with the with the pendulum. And so the mass was 0.402 kilograms, and the magnitude of length was 0.7 meters, and the initial position was negative 0.107 and negative 0.63 meters. And our initial velocity, we started from rest. And here we have our tracker data that we got, and let's take a closer look at that. So how do we determine the oscillation period? Well, the oscillation period is also known as the period, and so that is the time that it takes for us to get from one to the second. So this we can say is T1, or let's say T1, and so then we can say this is T2. And so when we look at this, we can see this goes from 3 to about 4.5, let's say. And so we can make a rough estimate, and that's a change in about 1.5 seconds. But that estimate we can determine that algebraically, and here we did exactly that. And we're using this formula 2 pi times the square root of m over k, and so that gives us 1.5197 seconds, which is pretty close to our estimate. So, we can do that algebraically. So how about the spring stiffness? Well, so we know that K is going to be equal to 4 pi times the mass divided by the period squared. And we can take a look at our graph that we have here, and we can tell that this is pretty similar to what we intend to get. And so that equates out to K is equal to 6.872 Newton meters. And so our relaxed length, we can use everything we've calculated so far, and we can get our final relaxed length. And so we did that right here, and that's our L initial. So let's take a look at the computational model and its initial conditions versus our algebraic equations. So the initial position was obtained from our tracker coordinates, which we used to determine using our video. And our spring constant was also calculated from tracker coordinates. And our relaxed length L0 is calculated from our F net and spring constant. Here we can see the computational model that we used to find these initial conditions. So let's take a look at the computational model for spring length and the energy. And so we have L is equal to the ball position minus spring position, and L hat is equal to L divided by the magnitude of L, which is going to be our unit vector, or direction vector in this case. And we have S is equal to the magnitude of L minus L0, which we have written here. So let's continue on, and let's find our energy systems. So our energy is going to be equal to K is equal to 1/2 the ball's mass times the velocity squared. And we know that is going to be K is equal to 1/2 mv squared, as I wrote down here. And this is going to also be, and we're also going to calculate for our gravitational potential energy, which is mgy, as we know. And our spring potential energy, which is equal to Hooke's law, so 1/2 ks squared. And adding all of those together will give us our total energy. So this is the computational model loop, and what this is doing is taking every time period that we have and calculating everything we need in each period of time and giving us a much more accurate answer than how we do it algebraically. And so here's the computational model loop, and here I have written the force of gravity is equal to negative mg, and the spring force of spring is equal to Hooke's law, or as we could say, negative k is SL. And then we're going to calculate the net force, which is adding those two forces together. Then we apply the momentum principle, which we had talked about earlier, and we use our velocity update formulas and our position update formulas to get our position and our velocity at each corresponding time. And so this loop will continue, and it will give us this computational model that we have here. So we can see that our computational model differs a little bit from what we had in our observed. And so some reasons why, some sources of error would be the system is not isolated from the surroundings, so there's work done by the surroundings that was not necessarily taken into account. And there's also inaccurate center of mass in tracker, as in tracker you have to put in every exact observed point as you find it, and that can be hard and can cause many points of error. So now let's ask, is the energy principle satisfied? That's our total goal of this lab. And we can see here that our delta E remains relatively same, and that the energy principle overall is satisfied, as we can say that delta E was equal to 0, and that our overall system conserves energy and follows the energy principle. And finally, let's compare the oscillation periods in the x direction and the y direction. So here we have 3t is equal to 4.938 seconds, and we can divide that by 3 to get our actual period, and we can use that to get our k, or our spring constant. And we can find here that we have 4 pi squared times 0.0402 divided by 1.646 squared, and that overall totals out to 5.858 newton meters. And we do the same thing in the y direction. We just change our period as our period changes in the y direction, and we do the same thing. We use the k, and we use and we find our overall k here. And we can see that k is going to be equal to 6.872 newton meters. So thank you. That's my lab 4 for physics 2211.